Thank you all for joining us today. I am so honored to be a representative for the UWIT Research Computing Division here, telling you about this service and how you can get it, how you can start using Tillicum, and some of the exciting things coming up with that. So Tillicum is really centered at this junction where you have all of these workloads that need acceleration or can highly benefit from acceleration. AI, of course, training large models and tackling these real-world problems, finding adaptations or new applications for all of us to use in our daily lives, as well as just learning and doing research about AI technologies. GPU accelerated simulations across all fields of science, really scaling up that to gain back your time to be doing research and leave the computing to Tillicum now. You can really gain some hours back and have your results faster and cheaper. We also have interactive workloads enabled on Tillicum. So if you don't have your code is ready, shovel ready, and it's more interactive, then you'll have a graphical user interface, which I'll show next a little bit about what that looks like, so that you can use things like Jupyter Notebook, VS Code, MATLAB. Eventually we'll be onboarding a lot of apps through this browser-based interactive graphical user interface. And finally, we'll be supporting common data sets on Tillicum. So this is just a list of the ones that are enabled right now, but we have a program where you can nominate data sets that are available or of interest to multiple research groups, and we'll store those for you. So they're already preloaded on Tillicum, and you don't have to wait a long time for those downloads. The work is already in your workspace. I want to talk a little bit about the hardware, and I do want to thank our team in research computing for having such a high-touch relationship with our vendors to bring you this service so quickly. It's really been a whirlwind 3 months to get to this point where we're launching next Wednesday for general availability. So Tillicum is a cluster provided by Dell and Redesign with NVIDIA GPUs. It has 24 Dell servers. Each of them have 2 terabytes of system RAM per node. And this is a total of 192 NVIDIA GPUs, and that's 8 GPUs per node. And each of those GPUs has a high capacity, so they each have 141 gigabytes of RAM. So we're really allowing you to scale. Maybe you wouldn't have to scale if you have a model that can make use of 141 gigabytes of RAM on a single GPU. That's done faster than ever. And we have multiple of these high capacity GPUs per node and across the cluster for scaling. The scaling is really driven by the NVLink, which is allows the multiple GPU communication at high speeds necessary for your research, and we have InfiniBand holding together the whole cluster. Finally, we have 3 petabytes of flash storage mounted to the server so that you have to the cluster so that you have your data when you need it fast. Finally, we were able to complete a top 500 benchmark, and that gave us about 8.8 petaflops, and a green 500 benchmark, which gave us around 46 gigaflops per watt. So we're really proud of these numbers. Talk a little bit about software. So Tillicum is a Rocky Linux system with Slurm as our job resource manager. We have Open On-Demand Platform, which is that graphical user interface, which I was mentioning before, where you'll be able to use your Jupyter notebooks, but with a massive supercomputer behind it. We support containerized environments with Aptainer runtime, which is also compatible with Docker. And we have LMod to support modules and Python environments, of course, with Conda module being kind of our central recommendation. Tomorrow, in the same place at 10 a.m., we're having a training, which will go through a lot of these a lot of these options and get you onboarded faster than ever to use Tillicum. And you get a little bit of free computing time over the weekend as well. So I just wanted to show a screenshot of what that looks like. This is what Jupyter Lab looks like everywhere, but this is running through your browser and connected to a PyTorch environment on Tillicum. So you don't have to learn a lot of new skills to remote your favorite program into Tillicum. We've already set that up for you. We're trying to lower the barriers to adoption of this service. All right, business model. So as Andreas was saying, this is a pay-as-you-go model, and it's charging on the GPU hour, which is calculated using the elapsed time of the job multiplied by the number of GPUs. And you have to request a minimum one GPU per job, so there are no CPU-only jobs allowed. And the rate is 90 cents per GPU hour for production jobs. And this will be billed monthly through our UWIT bill system. There's no charge for persistent storage in your project. You have dedicated project storage, each research lab. This will be 1 terabyte. And then you have temporary data storage for up to 2 months. And this has a 100 terabyte limit per user right now. And we will be constantly examining these policies to find the best fit for our user group. So keep your feedback coming. We don't charge anything for import and export of our data to any of our systems that UWIT runs on premise. And we have Globus endpoints set up for some of them, which I'll talk a little bit more about. Data parsing and manipulation are all available on the login node, so that doesn't cost you to use that. My favorite thing about Tillicum and what I think differentiates it from some other providers is that the job that you're scheduling with Slurm, whenever that is over, your charge on that job stops. So as long as your job ends nicely and you have your code running and then it stops, that's when the clock stops on your charge. So we're hoping that this limits some unexpected charges that you might face. Tillicum is not set up for long-term data storage. We have other options for that. Here's a little bit more about our storage tiers on Tillicum. So we have our project storage. Like I said, for each research group, you'll have 1 terabyte of storage. This is where you want to keep your code spaces, your Conda environments, everything like that, software just for your lab shared files. This is permanent and it's going to be backed up with snapshots. This is also set up as a Globus endpoint, and you have Linux tools to transfer data back and forth. Then we also have our scrubbed storage, which is our temporary storage with a high user quota. It's going to have a 60-day auto purge, and that's what we're trying to implement so that we keep this resource open for the community. Let me talk a little bit about Globus. Globus is a subscription that we bring to you. UWIT provides for our users that allows you to transfer files using a Globus resource from your personal laptop, from other endpoints around the world, and especially to Tillicum from Tillicum, and with our on our HIAC cluster and also our COPA S3. So we really recommend, because Tillicum isn't approved for long-term storage, we recommend having a portfolio of storage options that can allow you to move around your data so that it is stored in a way that is accessible and also in a way that meets with your data usage policies for your grants. So COPA is our S3 storage service. We call this our warm tier. We have bulk plans and a quota by quota or month by month plan, which allows for some flexible storage. And then we also have our Lolo tape archive, which is a geographically redundant backup storage solution that we bring to you here in UWIT as well. I'm going to be sharing these slides at the end so you can check out all of these storage options after this. So really the point that I'm trying to get across is, although we don't offer Tillicum for long-term research storage, by having a portfolio of services with UWIT, you can have the storage solution that best fits your needs. Finally, how do you get this service? Well, the service info is published in a knowledge base article on the UWIT website, so it.uw.edu. If you use the search bar to search for Tillicum, you will find this. Also, we have a service catalog, which says a lot of the same information. We have an intake form and a demonstration account form. So if you are not sure if Tillicum is the right fit for you, everyone's first 100 hours on Tillicum are free. If you're just testing out Tillicum, you have a little less storage, but you still get your 100 hours for free. And I'll talk about other special offers today in just a moment. I also am linking to the Tillicum system architecture and our user guides.
My name is Zoe Ryan. I'm a solutions architect at NVIDIA working on our higher education and research team. I've been with NVIDIA now like 5.5 years, and my main goal is to help support researchers like y'all who are using GPU clusters. So it's really a pleasure to be here today. I'm one person on a very large NVIDIA team that's been supporting the deployment. I'm actually kind of coming in at the last moment. You know, you're already over the finish line. Now I'm going here to give the workshop, but quite a few members of our team have been really involved with the bring up here, and it's going to be really exciting to see what y'all do with this cluster. So today, we kind of have a hodgepodge of things assembled for this workshop. I know there's going to be kind of folks from all ranges of interest in GPUs and all different backgrounds as well. Like hopefully we have some folks who are brand new to GPU computing. I know we have some experts in the crowd. I'm really just going to try to talk about like what software options we have that might help accelerate on top of the hardware that y'all are getting access to. So if you'll kind of amuse me, I'm going to be using the thumbs up to thumbs down range for a lot of questions during the talk, just to make sure we're all on the same page. Most of the time people give me the sideways thumb, and I'll take that as well. That's okay. But I want to just start with like a high level agenda. We're going to start with like, how does a GPU actually work? I think we sometimes get really wrapped up in our workloads, training big models, but it can be nice to come back to the basics and make sure we're all on the same page of why we care about accelerated computing, why it's useful. Do you think you have a good answer for how GPU works? Thumbs up is good. Thumbs down is I'm giving it a good guess. I should probably give a thumbs up. It'd be encouraging if I gave a thumbs up. Okay, this is awesome. Okay, so we have a mix of folks. We're going to go through a pretty high level, but I think it will give you an idea of like what workloads might really benefit from this type of compute. So we'll start there. Then when we're all on the same page, we're going to start talking about software. Hardware is obviously a huge component of this, but making sure you have the right software tools can make your job a lot easier, right? My goal as a solutions architect for higher ed research is to make sure you're spending as little time as possible trying to get our software running so you can focus on your research. So we're going to talk about some platforms that exist that you could try out for your own work. We'll try to keep it very broad because there's folks from every domain here, but I'm always happy to take questions afterwards. The last thing we're going to do is talking about getting the most out of your code. So if you're an experienced GPU user, maybe you already have a lot of programs that you're running, trainings that you're doing, running inference. At the end of this section, we're going to focus on how you can get the most out of your code, right? What tools do we have in our tool belt to make sure that we're getting the most performance out of the hardware that you all have access to? We're going to get the most for your 90 cents per hour. That's our goal. Okay, how do GPUs work? I think it's nice to start with a term that might come up quite a bit, right? Accelerated computing, parallel computing. It's everywhere. I think this is the type of thing that hopefully y'all are excited about doing. And one thing I think is nice to just get out of the way at the beginning is that it really is a marriage between two different hardware processors, right? Kristen mentioned you can't just get a CPU while you're getting your allocation on the Tillicum cluster. And that's because in the case of accelerated computing, you really need both, right? When we think about like my Mac, for example, it has a really great CPU in it, and it's been tuned over years and years of development and research to do serial tasks really well. It does things like gets my emails for me, I can respond to Slack messages. It does that extremely well. And what we're introducing in the system like Tillicum is the GPU accelerator. It's the other part of this kind of marriage between two hardware components. And the main difference for all intents and purposes is that the GPU is designed to do a ton of things at once, right? Your CPU is doing one thing right after another, it's chugging along. I like to think of it as like a person driving in a sports car. You're one person and you're going extremely fast. Whereas the GPU is maybe the less glamorous, but extremely useful bus. We've got hundreds of people all together, maybe moving a little slower, but we're all going at the same time, right? So these two things are working together. The plus sign is always like a little grayer than I want it to be. We're just trying to emphasize that these two components are working together. And the GPU here has a bunch of these green boxes, which are just the cores, right? Thousands of cores working really hard at the same time. So for GPU experts, they're like, okay, let's get past this one. But I think it's nice to just like even the playing field. This is what we're talking about. And it becomes really interesting to think about when is that actually useful, right? If you think of these abstract blue and green lines as your program, you might be thinking the GPU is the one running all of the code. Like actually not really the case. If we think about most scientific workloads in research, what we've found, and this always changes a little bit, is that really only like 5% to maybe 15% of your code really benefits from having this parallelization available, which is a little bit interesting, right? Because you think about the amount of potential performance benefit that you get when using a GPU can be like 100x, 1000x, but you're really only going through and modifying or optimizing a very small section of your code. So the thing I want people to keep in mind when we're talking about all the like software tools available for you today is that it's really a matter of finding the most computationally intensive parts of your workload and offloading those to the GPU, right? There's usually 5 to 10% of your code that is the biggest bottleneck. And if we can get that running really quickly on the GPU, you're way better suited for the long run. So just think of finding the biggest bottlenecks, things like FFTs, linear algebra, matrix multiplication, computationally intensive tasks, shove them to the GPU and keep the rest of the CPU running. That's our goal here. And we'll share these slides hopefully at the end. It's nice to come back to like, what are the things that we care about when we're trying to figure out if the GPU is for you, right? If it's for your workload. It's really a matter of whether or not the workload you're doing can be run at the same time, right? Some things lend itself really well to this. I mean, I've already used matrix multiplication, think of rendering images. All of those can be broken down into very small subtasks and run at the exact same time. So concurrency is like a big consideration when you're looking at your own workload and deciding whether or not you want to try to run it on Tillicum. And then really the thing that I always come back to when I'm talking to researchers is like, what is the goal in going on this journey of trying to get it to run on the GPU for the first time, right? Because not only are you going to introduce new software, you're going to like move over to a new platform, you really want to make sure that there's some benefit for you as a researcher at the end of the day. And there's basically 3 categories of things, probably only 2 that you really care about doing. Something that allows you to solve your problems faster, or something that allows you to solve bigger problems. If you can accomplish either of those 2 goals, it's probably worth looking at parallel computing. Okay, we had a lot of middle of the road for earlier about understanding GPUs. Did anyone move up a little bit? Did some people move down to a thumbs down? Okay, great. So hopefully we're on like more of an even playing field. That's the most kind of like architecture-y conversation I'm going to be having for today. I'm always happy to answer questions though after the event or in follow-up about some of those more details. But I think the software stack is an interesting one to then kind of center our conversation around. So it can be a daunting task to try to talk to a room full of researchers in very different domains about what types of things the GPU can be used for. Because I think we could probably talk individually about your research domain for like hours, honestly. I think the kind of cheat code to talking about software for the NVIDIA hardware stack is that anytime you see the prefix CU on any software library you're trying to install, it's probably a GPU accelerated library, right? So we've got up here cuDSS. We've got some that are outliers, right? But we've got also cuEquivariance, cuBinumeric, cuDF. It's just like telling you as the developer, you as the researcher, these are all CUDA accelerated, right? They're software libraries that are going to run well on the GPU. And if you come across them, it's probably a good thing to try on Tillicum. So I wanted to try to like hit at some categories that might be of interest for researchers here. Some of these are newer and some of them we've had forever, right? So cuEquivariance has been really interesting recently for folks doing more material discovery. I think it came out maybe 2 months ago. And then we have our longer standing projects like things like cuDF, which is like an accelerated version of pandas through the Python ecosystem, which we're going to talk about more later. This is all really just to get you thinking about the different domains that might benefit from using GPUs. And then we've got some like token, very ugly slides that I think are actually very useful. And this is like the overall breakdown of how the software stack works on GPUs. So on the left-hand side, what we have are all the possible ways you could get access to this hardware, right? You could have your kids' gaming PC that they play Fortnite on. You could also run your CUDA code there if you wanted. You could run it on the on-prem system like Tillicum. You could run it at the edge, whether you have like little Jetson devices, maybe collecting data somewhere, or you could run it in the cloud as well. The hardware here, we're kind of agnostic to where it actually is. Obviously, you're going to get better performance in some places, maybe a cheaper rate. That's just kind of up to you to decide. Our focus today is on Tillicum, but anything you want to test out, you could do at any one of these kind of GPU hardware sites. And then there's 3 categories of like, how can you as a programmer or as a researcher or someone working in a lab, how can you actually write code for the GPU? Right-hand side, we have CUDA, right? Like if you're wanting the absolute peak performance, how you can optimize every dial, tune every lever, that's where you're going to go to. That's our lowest level foundation. It's not only like the architecture for our whole software stack, but it also is sort of an extension to languages like C++, where you can really fine-tune exactly how many threads you want to use for your program. I'm not going to speak much on CUDA today, but it is always your highest performance option when you're going to write code for the GPU. Then we have a second category, which I think is always very interesting to talk to researchers about. On our team, we spend a lot of time working in hackathons where we meet with researchers for like 3 days straight. We try to learn something about their science domain, but really we just try to accelerate their code. And these types of directives are a really interesting way to do that. Has anyone heard of OpenACC or OpenMP? Some name recognition, never heard of it? Okay, kind of a split crowd again. So this is great. OpenACC and OpenMP are not parts of like NVIDIA. They're separate organizations that focus on taking older or legacy code bases and adding in acceleration after the fact. So something I see a lot is like I come and talk to a research lab. They're like, we have this code that's been in this lab for the last 20 years and we run it, but nobody knows how to make it run faster and it's a million lines. And it's a really unapproachable goal to try to make that run faster on the GPU. But with OpenACC or these types of directive languages or compile options, you can add these little compiler hints to your code to take the worst, least performance part of your code and accelerate it for the GPU. So it's kind of an interesting way to like dip your toe into the water of GPU acceleration without maybe trying to take over a whole code base in a language that you maybe don't understand. It can be a really great way to get some big performance benefits by finding that 5 to 10% of your code that is the least performant. So that's one option. Directives, I think of as just compiler hints, right? We're telling the compiler, hey, compile this for the GPU. We want this part to be parallelized. That's really all we're doing. And then where we're actually going to spend like a little bit more time today is in just standard language parallelism. So this is where you as a developer or someone who has a really big preference in what language you want to write in, you might want to be paying attention. I'm going to focus on Python today. Hopefully that's the right option for the crowd because we have a lot of new libraries from NVIDIA and also from the open source community that help you use Python on the GPU. So people like, I see some nods, which is good. Python. Someone wanted a CUDA talk and I'm sorry to not be giving it to you today, but I'm happy to do it another time. This is where you can get some parallelization directly in the languages you're already using, right? So most often than not, I'm working with a researcher who's writing NumPy code, who's using scikit-learn, who was undergrad who's been writing Python code forever. And we want to take that and make it run on the GPU. We're going to focus a little bit more on that. And then the big green bar is just telling you that under all of this, it's basically running the same code, right? It's all built on CUDA. It's all using our kind of foundational architecture. It's just about how you interact with that actually at the end of the day. So we'll go to my like Python section of the talk. I want to just talk about like big picture libraries that might be useful to the general developer who's going to take advantage of Tillicum in the future. Are people NumPy users? NumPy, used it, don't like it, haven't heard of it, great. Double thumbs up is excellent. Okay, so I think maybe when I first used NumPy, I don't even think I really realized it was separate from the actual Python ecosystem. It's so embedded and ingrained in Python that it almost appears to be part of the standard Python language. But if you've ever used an ND array at all, you've used the NumPy library. And it's been around forever, questionably my whole life, I think. And it's extremely well tuned to perform on CPUs. When you do benchmarks that compare raw Python code to NumPy code, you already see a massive benefit in performance. So NumPy is almost, I think, the most pivotal library on the Python ecosystem. Everything extends off of it. And what the CuPy community has done, which is an open source community of pretty awesome developers, it's not an NVIDIA library, but they've taken the interface that we all know from NumPy, such as the ND array, ways that you can do modifications on those types of kind of data storage options. And what it does is it takes that API and it applies it to the GPU. So let's say you're a user who has thousands of lines of NumPy code that you run on your laptop, and you're like, it's starting to get pretty slow when I want to use it on my full data set. What you could try out would be to try the same code just using the CuPy implementation, right? So the goal is to do like a zero change copy from the NumPy code to the CuPy code. So instead of having our ND array on our CPU, we would have it on our GPU. And under the hood, some very smart engineers have written all that code to run on the GPU for you. So it's like the easiest lift you could imagine as far as when it comes from taking something running on the CPU to the GPU is if you could use the CuPy library. Has everyone heard of CuPy? If you've heard of it, thumbs up, brand new, thumbs down. Okay, also mixed. That's awesome. I think the question I always get without fail is, what if I want to run something on my laptop sometimes and on Tillicum sometimes? It's a great question. You could do like a variable import statement, right? Check if your GPU is there. If it is, let's import CuPy. If it's not there, we'll run the NumPy version. So it can be pretty flexible when you're doing that type of like testing of your code base. And the slides keep giving it away. I forget there's a timer on this one every single time, and I never hit the time right. But I want to show just a quick example, right? Let's check our sanity with what I'm actually talking about when I say API alignment. On the left-hand side, we have some initial NumPy code where you're importing a library, creating a size, creating your matrix and running some linear algebra function, something from the NumPy library. What we're talking about when we're talking about moving from the CPU to the GPU is as simple as importing the other library. We're being good developers here. We're not just importing CuPy as NP, we're changing it to CP and running the same code. In this very contrived example, we see a 50x speedup, which is excellent. Obviously, it really depends on the type of thing you're running, but it's just one example of how the lift from one library to the other is relatively light. And just for the sake of robustness, I think it's nice to take a little quick aside of like, what is the downfall of this? Because I've given you the promo slide. I've said 50x speed up on one line of code. It's also nice to talk about like, what are the considerations when I'm actually using this in my code base? And this flowchart really describes what's happening under the hood in a pretty clean way. Has anyone heard of just-in-time compilation? Haven't heard of it. Or JIT compilation? Okay, great. Lots of people have heard of it because it's not just something that happens during the CuPy utilization. It's actually really common and is part of all GPU computing. What we see is when you go for the first time and call like the sum function, right? The sum kernel from CuPy, the compiler, the Python compiler that we've introduced is now saying, is this the first time I've called this in my Python script? And if it is, what it does is it takes it and compiles it into like fast machine code for you to use. It's not really relevant to us what it actually is, but it's there, it's cached, it's ready for you to use. So if you have a Python script that only runs that code one time, you've actually introduced a new kind of bottleneck into your code because you're now compiling and caching the code on that first iteration. But let's say you want to run this sum code 1,000,000 times, 1,000 times, something relatively large, then the next 999 times, you get to go and run that actual fast code under the hood. So just-in-time compilation refers to the fact that when you need to run that function the first time, it's going to compile it and cache it for you, and you pay that one-time toll then to get a massive performance benefit down the line. So the high-level note here is the GPU needs a lot of work to do. And this is just another example of like, if you give it one command on a very small data set, it's going to be slower. But if you give it a ton of data and you run it 1,000,000 times, it's going to be much faster. So hopefully that's resonating with people. This is actually pretty foundational to GPU computing in general. It's just like a good example of how it works in this specific library. Okay. This is like a quick aside because I think it's nice to talk about resources that are available. I think as a solutions architect for higher ed, a lot of the time I spend is kind of deciphering our NVIDIA documentation to try to help the end user because there's a lot of it. It changes a lot, and it can be really helpful to have someone just point you in the right direction. One effort I'm really proud of that we've been working on quite a bit is providing more completely open source notebooks for learning this type of content. So we've introduced something called the Accelerated Computing Hub. This is just one example, right? We heard Kristen talk about how you can use Jupyter notebooks directly on Tillicum. This would be a great example of a way to use your like first 100 hours of trial to see if this is worth it. This notebook just walks you through CuPy, right? So if you're brand new to it and you're like, oh, let's see what it's all about, you can go up here and try it out. On the left-hand side, though, we also have other libraries that would be useful if you're interested in Python. Numba is a pretty cool one. Has anyone heard of Numba? There's a lot of names that sound pretty familiar in Python, so it's also hard to tell, but Numba is pretty cool because it can run on CPU or GPU, and it basically just allows you to do that just-in-time compilation for any function in Python. So if you were really like excited about the just-in-time compilation or JIT compilation idea, Numba might be something interesting to try. Okay, we have our like baseline. If you're using Python, if you're using NumPy, there's some options for you to get some acceleration early on. Now we're going to focus a little bit more on like data science workloads. The nice thing is that it just builds on what we've talked about, right? It builds on the Python ecosystem. And Rapids is basically a collection of as many of the Python libraries that we could from NVIDIA take the API and make them run on the GPU. Has anyone heard of Rapids? It's evolved a lot over the years, but it really kind of started out as an effort to take things like pandas and scikit-learn and bring them to the GPU. So if you're a person who's using a pandas data frame or has seen that in your life, then a really good option for you might be something called Rapids cuDF. It's the CUDA accelerated version of that data frame. So what that means is that if you have a bunch of structured data that you take as a data frame and then you do some like clustering algorithm on your laptop, that might be a really common thing to do with your data set. You could do the same thing, but scaled up quite a bit larger on the GPUs that you have available, but not have to change your code. So think of NumPy as to CuPy, like Pandas is to cuDF. It's actually even gotten easier. We've worked with the Pandas team now to do a zero, like you don't even have to change the code at all. You just load the extension and it will turn all your Pandas code into cuDF code, which is a really cool improvement. They've made something that was easy even easier. So you can do all the like messiness of your data loading and ETL in a data frame still, but just running on the GPU. Then let's say we're looking at like what is maybe the process of a data scientist, right? You're loading your data in, cleaning it up, you're doing some training, clustering, some learning on the data. And that also can be accelerated by the same library. Rapids has an effort to try to use all of the things that are in scikit-learn, which is huge, and make those also run on the GPU. It's important to note that each of these components has to be on the GPU for this to make any sense at all, right? Because if we load our data into the GPU, but your algorithm then has to run on the CPU, we're introducing a whole bunch of bottlenecks everywhere. So we just want to make sure this whole pipeline can be accelerated. And Rapids, at the end of the day, their goal is to make sure that the whole pipeline can be accelerated. So at the end, we also have like some newer things. You could run inference, for example, or you could do, our images are blocking it, sorry. You could also run more of a vector or graph search algorithm as well. These are all part of the Rapids ecosystem. The green box on the bottom is just highlighting again, it doesn't matter what hardware you're running on, these will be able to be installed, but will just run better the more hardware that you give it. Okay, I think the swim lanes like analogy here is a little bit hokey, but it is kind of nice, right? You can imagine that if you're like a little bit of a newer swimmer like myself, you're not very good at it, there's a lot of options for you that are zero code change. How can I take things I'm already doing and use the GPU without having to like make a huge lift? That's where we see like the pandas to cuDF example. As you go down, right, we introduce more changes, things you have to be doing yourself. Maybe it requires a developer on your team. And all the way at the bottom is where we see the actual CUDA development. So you're going to be somewhere in this range. A lot of times we see people starting with the zero code changes and moving down as you're trying to optimize your code further. So there's something for everyone is, I guess, the goal of this slide, right? It's not about where you are in your like development journey. There's a way to get into the pool and try out the GPU kind of at any one of these software stack levels. And in that same vein, there was a little bit of discussion in Kristen's talk about like having data sets available. There's a lot of things out there you can do to kind of jumpstart your development, right? And we have this thing called NGC. It's really a misnomer for what it is. It's called NVIDIA GPU Cloud. It's not a GPU cloud. It's really a like app store or repository of useful GPU stuff, right? So the first example I always think of is like, let's say you want to use a pre-trained model and you want to just fine tune it for some workload that you have. You probably don't want to just go search anywhere for it. You can find the one that you want, hopefully on NGC. So they have frameworks, they've got toolkits, they got models, all of it is available on the page. They actually recently redesigned it. This is what it looks like now when you go to it. I went recently and I was like, this is not the NGC I know, but it all has the same content still. So it will show you like the highlights of what people are using. You'll have to give us your email to use this. You have to sign up, but once you've signed up, then you can get access to all of this. So we'll give you a container to run PyTorch, to run an inference server, to run CUDA. All of this is like the software things that you want to be easy to use. Hopefully they are if you go here and you can install them. So these are just some examples of ones people are using the most often. I want to dive into like one example that I think is probably the most used, and also the question I get the most is around PyTorch performance, right? We have researchers across every domain that are using PyTorch. They all have different questions on how we can optimize, how we can scale, how we can do distributed training. And I think it's important that we start at square one with the most performant option, right? So you can go to pytorch.com. Maybe that's the website, I don't actually know, but you can go to PyTorch and you can download their container and you can run from there. If you're running on the Tillicum system and you're trying to use the most up-to-date GPU version, I would suggest you start on NGC, because what we have is behind the scenes, very smart NVIDIA engineers are optimizing everything for our newest hardware releases, right? So what you'll see is that year after year on the same GPU, you'll get better performance out of the software due to the changes that NVIDIA engineers are making under the hood. So I always try to highlight like they're keeping them up to date. September 29th is the last time this PyTorch container was updated. And then it will also show you commands on how you can run that. So we heard mention that y'all are using Aptainer, compatible with Docker though, so there's good instructions for how you can kind of convert between each other. So PyTorch is like the least glamorous container you could highlight in this demonstration, but it's actually probably the most useful for like the broad audience. It's nice to know that there's like a lot of stuff in this container as well, more than just PyTorch, right? So if you're wanting to do some of those taxing ETL operations, there's good support for the Dolly library, which allows you to like help do data loading, data processing. The real note is that when you go to the page and you look at the container, it will tell you everything about how you install it, what's under the hood, what other libraries come with it, right? So any of these CUDA, cuBLAS, cuDNN are all things that come with that same package. You can also look by use case. I find this is like less often used, but is maybe still useful for folks who are just trying to find which area they want to kind of use their data in. So if you're like broadly speaking interested in things like image segmentation or video analytics, you can come to these pages also on NGC to find good like Python-based Jupyter notebooks and examples for you to walk through those same workflows. So if you're maybe here and you're like excited about using Tillicum, but you haven't really used GPUs much before, this is a great way to get some inspiration on types of workloads that the GPU does really well. Okay, we're down to our last section, and I'm not exactly sure when we were supposed to end since we started early, but are people feeling better about the software stack? Does anyone have any questions before we move on past the software stack. Yeah. Yeah, that was a great question. I'll repeat it for the people online. Question was, is TensorFlow supported on Tillicum? Yes, it is supported by NVIDIA GPUs. I was just going to show this page again. Honestly, we're seeing less support for TensorFlow going forward just because everyone seems to be using PyTorch, but there are still containers on NGC. If you ever have any questions, it's actually a good point. I was going to show what it actually looked like. You can always come and look in the NGC catalog. This will show you everything that's available. You can look at just containers, and I'm sorry, this is probably small. And it will show you all of the ones that are available. So this is just, I'm on the guest Wi-Fi, I think, sorry if it's slow. This is where you can go to actually find the containers at the end of the day. Let's see if this will load. Is there any questions also while we're looking about software? Okay. This is not a good demo of this website.
Will you have your slides available for
Yes.
us after?
Yes, I will.
I'll send them.
Yeah, and I'll put the links in there as well. But yeah, so TensorFlow, sorry, that's all I was trying to show. In the same category as PyTorch is available. You can see it's updated less frequently just because it's used less, but the same place you can come and get all the information that you would need around how to run it. Great. Okay. So we've talked about how the GPU works. We've talked a little bit about the software stack. I'd be remiss to say that's like a comprehensive overview of all the software that is provided through the NVIDIA like CUDA stack. I'll be here afterwards if you have questions around like your specific use case. I'd be more than happy to discuss it, but hopefully that sets the scene for all our Python users of ways you can get started. Now I'm going to like switch gears a little bit. Let's say you're a person who's already been using Hayek, you've been using maybe cloud resources, you already have used the GPU quite a bit, and you're trying to make sure that going forward, you're getting the most out of your code. We're going to talk a little bit about profiling. Has anyone here profiled their code before? Doesn't have to be comprehensive, just profiled it. Okay, someone's like, I know I should, and I haven't been. Okay, well, I think it's a good place to start is like, when is the right time or why should we do it? If you're brand new to profiling, it's a way that you can get, in the case that we're going to talk about, like a visual output that shows you the areas in your code that you could get performance, like you could improve performance, right? So let's say you've already done some proof of concept work, you've tested things out, maybe you have your first deployment, and you're looking at the next generation of the code that you want to work on for your research. In that iteration cycle, it's probably the right time to start looking at whether you can squeeze more performance out of your workload, right? At the end of the day, you are you're still paying to use the resource. It'd be great if you could use less of it or use it for something else other than just kind of wasting time on something that's not optimized, right? Step one is always make sure it's correct, right? We do these hackathons a lot and people will change a crazy amount of the code before they check it again. And I'm like, well, we have no idea if this is right anymore. So goal number one is make sure that the code is still working correctly. And then after that, we can start looking at some optimization techniques. So this is not your first step. This is like your third step down the pipeline. This is how we actually start getting some maybe even bigger speed ups based on what you started with, right? So it's all a cycle. We're going to analyze, look at parallelizing, then optimizing as well. And there's a lot of different like types of folks who are hoping to do this work, right? And it's interesting to see how like in our corporate slides, they brand researchers versus folks who are data science versus sysadmins. I noticed in my time working with higher ed and research that folks are actually having to do basically all of this, usually if they're a researcher. So I'm going to try to talk to like the different options that we have based on where you might be in your actual profiling journey, right? So in our kind of cartoon of a researcher, you're most focused on doing things fast. You want the most performance and you're across a bunch of different domains. Data scientists might be more focused on reducing training time, cutting costs on the amount of compute you're going to use. All this to say there are different options based on like what you're interested in doing, right? So I think the thing I use the most when I'm working with higher ed and research is something called NVTX. Has anyone heard of NVTX markers? Something you might have used? Okay, cool. This one might be a new one for a lot of people. NVTX is basically similar to the decorators we talked about before. It's a way you can add in little context clues into your Python script to tell you when you go and profile some interesting details, right? So let's say I'm really concerned about my training loop. I'm like, this is really slow. I know that this is where my like speed up could come from. You can use these markers to highlight in your code what those areas are so that when you go to profile, you can see them very quickly. So it's a useful way to get some insight to what's actually happening in your code. Because I feel like we all know that you may have an idea of what is slow in your code, but it can be actually really hard to pin down where that is. And you don't want to just be adding like a million print statements or something to try to figure that out. DLProf is a way that you can look more at like the deep learning side of things. There's also really great PyTorch profilers, like separate from the NVIDIA stack if you're using PyTorch to look at those. And then on the sysadmin level, we're going to talk a little bit less about that today, but that's how you can make sure like the overall health of your system is performing well. So now we have like the suite of options that you should try out if you want to profile your GPU code. For today, we're really going to talk about nSight systems. It's the kind of first step that you could take to get a comprehensive look at how well your workload is performing. So let's say I have a Python training script that it's PyTorch or something. I'm loading in my data and I want to see like where the bottlenecks are. The nSight systems GUI, which I always think it looks like GarageBand, from like a 50-yard distance, it looks like we're mixing together some music, but this is what the GUI will look like. And it will tell you not only what's running on the CPU, what's running on the GPU, and it will really help you find the gaps where your GPU is doing nothing. We want to avoid GPU starvation. It's extremely dramatic to call it that. But we want to avoid any time where our CPU is doing something and our GPU is just sitting there, because you're still paying for those hours, right? You want to make sure it's getting used all the time. And so it's a visual way in which we can get insight into the whole workflow. It's really useful, but can be a little daunting at first look. So if you're wanting to go like the next step in, let's say you're writing CUDA code and you're like, this kernel, I think is the problem, then nSight Compute is how you can get into the weeds, really look at your kernel and make sure that it's the best, most performant option. I really have not stepped much into the world of graphics, but there is a whole nother profiler for folks who are interested in doing some more debugging on graphics style workloads as well. So again, we're going to start at nSight Systems, and then once we're kind of on the road with that one, we'll go ahead and see what the next options are. So nSight Systems. You really don't need to pay too much attention to the right side. I just think it's useful to have up there for us to kind of talk high level what nSight Systems does. Really what you would do at the end of the day is you would profile the code on Tillicum using like a command line option, running your script. And then from something like your Mac or your own desktop computer, you would download our nSight Systems GUI, and then you could analyze it and see what's going on, right? So it basically is like a file that you output that allows you to see individual calls running on the GPU. Huge highlight is that it's system-wide. So let's say you're brand new to GPU computing, you're thinking it might be worth it, but you're not sure. You could profile something that is just running on the CPU, and it will tell you what's running kind of still in a comprehensive fashion. Really, I think the main goal is if you're like a visual learner at all, it can be really helpful to look at this GUI and see if it's an all-white column, that means that nothing is happening on your GPU, and you should look at that section because something is waiting for something to finish. And that can be really hard to figure out if you're not looking at it in this type of manner. At the end of the day, really, though, our goal is for you to be able to see these changes, run the code again with some fixes, and then hopefully you can see visually that it's made a difference on the timing of your code, right? So we're going to actually go to this one, and I realize it might be small. Can you all see that at all? Yes, no? I was sitting in the back, and I have very bad vision, though, so okay. On the left-hand side, basically what this is showing us is all the categories of things we care about. So the top thing that we have is the CPU. It will tell you everything that's running on the CPU. Useful information, right? It's a team between the CPU and the GPU. Then below it is where we actually have the information about our GPU. You'll notice the NVTX category. That's where we can put our own markers in to try to delineate like different parts of the workflow. So for example, you can see this is a training script. Someone has labeled the forward and backward paths so that you can see where those are happening in the code base. And then at the bottom is where we see actually important information around what is happening, right? How much time we're spending in kernels. That's how much time we're like actually computing something versus how much time we're spent on like memory operations, copying things back and forth. The very bottom, it's not showing my favorite view. There's a view called Expert Systems View, which I think is like the perfect place to start because it basically looks at the whole profile and it says, if you had an NVIDIA expert there with you, what's the first thing that they would say? So that's where I always start. If there's anything horrendously wrong, that section will point it out for you. Like, let's say your GPU utilization is 5%, it will tell you. And that's a really good place to start for someone who's newer to looking at these profiles. So this is an ugly one to look at, but I think it's worth kind of like taking the time to look at together. I just wanted to quickly show like what they can actually look like. It's not worth going through a demo together, but you can see here, there's these big white columns. This is what we're talking about, making sure that the bottom half, there's something running on our GPU, top half, not so much. And then at the beginning, for example, we've got not much going on at the very beginning. This is usually like library load time. We're waiting for something to import. We're doing some data loading. It can be really visual to see it this way. Okay, I had one last thing I wanted to show. Is anyone brand new to GPU computing? Day one, day zero? Okay, great. I wanted to show like one last super getting started thing we have. We call it the build.NVIDIA page. In an effort to try to make open source models and API endpoints available more readily on the GPU, we've tried to house them all on this page as fast as we can. So let's say, for example, you're really interested in like the new Quen models, but you don't want to go through the process of like downloading it locally, spending your GPU cycles, like using your API tokens on your own system. You can test them out in the cloud, like in the NVIDIA cloud, just to get a sense of how it works, right? So if you were looking at Quen, you're looking at other models and you want to just try them out, you can go ahead and try them directly in the cloud without having to pull it locally. Let's say at the end of the day, you really like that model, it's good for your use case, then you can actually view the code and have it running on Tillicum at the end of the day. So this is just like a toy example of the Quen model, but there's other more fun and more interesting ones to try out. If you're looking for a way to really explore what is the brand new open source models available that you could run on GPUs. So I'll share the slide with links for anyone who's interested. And I'll leave it on this last slide with my email if you want to reach out about the research you're doing. Our goal in the higher ed team, there's 10 of us on the solutions architect team who are really trying to make sure that researchers are getting the most out of their GPUs. We have folks who are domain experts in specific areas. We have more generalists like myself. So if I don't know the answer, I'm happy to try to find the right person. But thank you for your attention and for your thumbs up throughout the talk today. Yeah, thank you.
Thanks very much, Kristen. It's a real pleasure to be here. You hear a lot of groups thanking everyone, and I just wanted also to thank both Research Computing, UWIT, and the university as a whole in terms of investing in this wonderful resource. And in particular, I think this is the way that when we collaborate, we actually have a bigger impact, both across the campus and nationally and internationally. So my name's Andy Connolly. I'm the director of the eScience Institute. eScience is an institute that supports data science and AI across all 3 campuses and across all research fields. So what I'm going to do is I'll tell you a little bit about some of the programs that we run through eScience, and in particular, those ones that are specifically in place to help you in terms of getting into large-scale computing, GPUs, or AI in general. And then at the end, I'm going to leave you with some of the training programs that we put together with UWIT to support onboarding and learning how to use and optimize the use of Tillicum for your research. So before I went go into this, we were actually the early users of Tillicum, and I just wanted to say how exciting it was from my own research. So what we work on are large astronomical surveys, in particular surveys from the Rubin Observatory. And the Rubin Observatory is going to observe half the sky 1,000 times over 10 years. And if you're looking at the same part of the sky over 10 years, then you can see objects that move across the sky. And so what we work on is detecting and identifying those objects, asteroids in particular, out in the outer parts of our own solar system. And we're not actually looking for the objects that you can see very easily moving. We're looking for objects that are below the detection limit of any individual image. And this allows us to identify asteroids that might be halfway to the Oort cloud, or to identify if there's another planet, say planet 9, in the outer parts of our solar system. So Dino Bektesovic, who's a postdoc working in my group, was one of the first users of Tillicum, had a really great experience. In 2 days of working on Tillicum, he processed more data. We were using CUDA for this. He processed more data than we managed to do in the previous 3 months. And so we're actually beginning to identify, as you can see on the right-hand side, we're beginning to actually identify asteroids beyond Neptune and beyond Pluto. So eScience, and this really is what eScience is about. It's about how do you take research ideas and optimize them for computationally challenging or complex data sets and make the research actually accelerate the research so we get to the discoveries earlier. eScience resides in the Physics and Astronomy building. We're on the 6th floor. This is where we hold most of our events, so our workshops and training programs, and where we hold the office hours. The eScience Institute is staffed with a team of really extraordinary data scientists and research scientists. These are computationally deep researchers who come from a very broad range of backgrounds. So this is oceanography, it's health informatics, it's anthropology, it's computer science and physics. And so they're multilingual in some ways, right? So they can talk about the different techniques, and they can tell you about techniques from different fields that you can bring to bear on your problems. And so they're very adept in terms of accelerating research across a broad range of research fields. We also have a team of software engineers as part of the Scientific Software Engineering Center, SSEEC. Many of these engineers come back from industry with 10 to 15 years of experience. And they, as I'll mention a little bit later, they're working on how we can bring robust software engineering practices into academia. So in terms of how can we help you as you start using Tillicum, and more generally in terms of your data science and your AI needs. So there's a number of programs that we run that I just want to run fairly quickly through and encourage you to apply to. One of them is office hours. Office hours, you can go use this QR code, go online and look up the data scientists, research scientists, software engineers, and look at their expertise, whether it's in Python, or it's in high performance computing, or it's in statistical analysis or SQL. Just reach out to them and schedule 20 minutes, an hour meeting just to discuss the problem that you're trying to solve. We also run drop-in office hours. So one of the ones we're very excited about is with UWIT, with the research computing, and that's on high performance computing. And so we run those every week throughout the winter quarter, and the schedule you can see there. And you can just come in and there'll be someone there who can meet with you and talk about how you want to interact with, say, Clone or Tillicum, or if you have any challenges with machine learning or AI, and people are there to actually talk through the problems. We also run a range of training workshops, and a lot of our workshops are informal education. So we're trying to fill the gaps between the undergraduate and the graduate education programs. A couple of those relevant for Tillicum are a new program that we just launched, which are the ABCs, or AI ABCs. So this is introductions to supervised and unsupervised learning and using neural networks. We were supposed to advertise it today, but we announced it a week ago and it filled up within a week. But we will be running this probably every other quarter throughout the next couple of years. But one of the programs that we have just announced this week is practical deep learning workshop for working with images. And this is 6 sessions starting on October the 15th. Running through segmentation, neural networks, model selection, and different ways of actually working with images. And what we've been developing for the winter and subsequent quarters are other programs, such as how to use language models in programming effectively, how do you take agentic AI approaches and embed them within your research workflow. We're very interested and excited about hearing your interests and needs in any of these spaces about data science, about AI, about agentic approaches, because if you have a need, there's probably 50 other people on campus who have the same need, and we're interested in trying to build out these programs for you. The Data Science Accelerator is a program we started last year. So it's a data science and AI accelerator. And this is an easy way of just filling out a 2-page application of a problem that you want to solve. And you get to work with our data scientists, our research scientists, and our software engineers. And these engagements could be really short. It could be for a week. Maybe you just want to get up to speed in developing a new machine learning model. Or they could be deep dives where you need to accelerate and develop new algorithms and methodology for the data sets you're working with. We're open to both of those. We run this throughout the year, every quarter. As I said, it's a short proposal, a couple of pages, and then we reach out to you to understand what your needs are. And then we match up the needs with the actual expertise that we have within the eScience Institute. If you are interested in this, then the next round for the proposals is October the 26th. There's a link here that you'll get with all the slides for how to actually submit the proposal. As I said, we run it every quarter. And we've been running it for about a year now, and we've had over 80 applications, and normally we can take about 6 groups per quarter. And these range from everything from understanding hospital readmission through to updating source code, historical source code, to the latest Python standards. The last couple of areas I wanted to just cover are, as we begin to rely more on software to address the data science and the data intensive challenges that we have, we also rely on that software being reproducible and being robust. And so this was the creation, or the justification for the creation, of SSEEC, which is the Scientific Software Engineering Center, which is supported by Schmidt Sciences. And here, as I said, we bring back typically experienced software engineers, often from industry, to bring them back to work on accelerating and improving the underlying software that we use for our research. There's a link here to engage with SSEEC. We're very open and interested in engaging with research projects, even at the proposal stage, where you are proposing to one of the federal agencies. We're very happy to engage in you to work through what are the software engineering needs that you might have to support that research. For Tillicum, I'm going to end with the sets of trainings that we have put together for the winter quarter. And then we will be extending this, for the fall quarter, and then we'll be extending this into the winter and the spring quarter. So tomorrow we have the Tillicum onboarding training, so getting up to speed and working with Tillicum. On the 15th, we have our deep learning for image analysis, which is our pixel proficiency workshop. We have a range of different programs that have been put together in collaboration with Research Computing and UWIT. And this is everything from text as data through to using containers, whether you're using Docker containers or you're using containers on Tillicum. And as I said, we're particularly interested in hearing from you, and you can either reach out to us through our contact on the website, or you can speak with us in our office hours to hear about what are the training programs that would be most beneficial for you to be able to optimize how you use Tillicum, how you use a clone, and really how you engage in data intensive or complex data sets or data science and AI across the campus. And this can also include, we have a lot of expertise in how do you educate in this space. So it could be, how do I train my lab and my graduate students to best be able to utilize these tool sets. As I said, the trainings and the workshops that we have planned for the fall quarter are all listed here. All of the links in this slide will take you to the details of those training programs and the registration process. I encourage you to sign up as an affiliate with the eScience Institute and sign up for our mailing list, and we will be sending out updated lists of trainings that we will roll out in the winter and in the spring quarters. We're very excited about this. We're very excited about the resources that are made available. And just speaking for my own research, we're already seeing the benefits of being able to accelerate the research that we're doing with these resources that the university is providing. So with that, I'm going to stop. If you have any questions, I'm happy to take them, but then I'm going to pass it over to Ting for the panel.
Thank you, Andy, for fantastic introduction about eScience. And we value very much the partnership between OR, IT, and eScience. So now let's move on to the early access user panel. And I'll be the moderator, and we have 3 panelists. So Professor Xiaosong Li, a Dalton Endowed Chair in Chemistry, and also a Senior Associate Dean for Research in Art and Science. So second panelist will be Mariano Gabito, sorry about that, Assistant Investigator in Allen Institute, and also an affiliated faculty at Department of Statistics. And the third panelist will be Rachel Ghosh, who is a postdoc fellow at a Dirac Institute. And I would welcome our panelists to come here to the stage. And in the meanwhile, I would like to introduce some of the early access statistics. So during the early access period, we have involved more than 100 users across the 3 campuses and having 40 principal investigators, and half are from COE, a quarter from CAS, and also from a quarter from School of Medicine, iSchools, Public Health, and Tacoma also. So there are also exciting user testimonies that we would like to show here. And in general, our users are excited about the perspectives that Tillicum offer for our research computing going forward. So without further ado, let me go into the panel session. So you will hear from 3 researchers and leaders, as I introduced, who been among the first to use Tillicum. And our goal is to share real-world experience and the strategies that help our community understand what Tillicum makes possible. So the first question to our panelists is that, from your perspective, what unique advantage does a high-end GPU platform like Tillicum offer over other platforms, existing platforms or platform on the cloud?
Mariano Gavito from the Allen Institute. And I think that the compute power and the particular GPUs that Tillicum offers are great. They are order of magnitudes better than what it's available in other clusters, at least at the Allen also. So in my case, the particular capabilities of Tillicum enable or fast forward my research like really like a bunch of months, like 3 months forward, like just by having the particular capabilities, the H200 GPUs with certain memories, the ability to load more data into them, faster compute, and in part also by the support of the team, no? But in this early process, but yeah.
I think for us, we tested out 2 different kinds of algorithms. One was just GPU accelerated machine learning using something like PyTorch, and also another class of algorithms which were just using CUDA acceleration without any machine learning kind of component. And for both of us, there were 2 things. One is just we regularly use Clone, which only has the A40s, or we have access to some A40s. So the H200s, of course, give you some order of magnitude improvement. For us, processes which would take on A40s on the scale of months take days on the H200s. And because this, I don't know how long this will persist, but also because this was early access, the memory access times were extremely good, because we often in astronomy, we are constantly loading and sending back little Post-it stamps, which incur a lot of I/O back and forth. So that was also very good for us on Tillicum. And I don't know enough about how the hardware was set up, whether Tillicum is especially good at co-locating the storage and the compute, but that also worked very well for us.
I was told that that there is a flash drive, but I also experienced the same, and they told me there are not so many users, so it was extremely fast.
I think I want to present my perspective as scientist instead of the dean. So I do quantum machine learning. So this the infrastructure allows us to build more layers of quantum logic gates, so that we can do a multi-layer, deep layer quantum machine learning algorithm. But another aspect of this one is this H200 has much bigger memory. So this will challenge my students and postdocs to redevelop the algorithm, to re-optimize the algorithm. So I think whenever we get a chance to optimize the algorithm for a new architecture, it definitely oftentimes brings in new ideas, new perspective, a new research direction. So I do think this is an opportunity for us to develop something exciting for this new infrastructure. But I do want take this opportunity to call someone's name. Eric Lomberg, are you still here? Yeah, I want to give Eric a big shout out. I think this is we didn't get to finish this big project, and I'm so happy like Xiao and Ting were able to develop this exciting GPU infrastructure. But this is a dream that Eric had for a long time, and we were not able to do that. So I think this is the concept and idea really started from Eric's leadership when he was still IT. I don't know where he is. But anyway, I do want to take this opportunity to give Eric a big shout out.
And for your context, actually, Xiaosong was the Associate Vice Provost for Research Infrastructure before me. And Eric was before Xiao as an AVP in UWIT. Yeah, Eric. Yeah, thank you. Yeah, and I'll be a little selfish providing some of my own insights, joining a panelist. So according to our test, so H200 in a machine learning task for many-body wave function is about 4 times faster than a 800 node on NERSC. NERSC is basically a computing center sponsored by DOE, and they often have latest technology and hardware as well. So H200 does have some edge over computing nodes like 4 years ago. And also the bigger GPU memory on H200 allows a bigger batch size, which allows neural network machine learning model training to have a higher efficiency. Yeah. So if there's any question from the audience, feel free to chime in and ask the panel as well. Thanks. Okay, so let's move on to the next question. So now, Xiaosong, you are no longer a faculty, you are sitting as a dean. So from a leadership perspective, how do you see shared resource like Tillicum supporting research at UW, especially in the emerging research needs across different domains?
So college arts and sciences has 4 divisions, very different. So from natural science, social science to art and humanities, very different. And all researchers in these 4 divisions have very different need and demand. I think this platform provides for natural science and to scientists like me, I think there's an opportunity for us to bring our A game, to compete. So that's an excellent. For the 3 divisions, I think this is an opportunity for them to adapt, to learn, to bring new concept, new research idea into that domain. And I think, as Mari mentioned, that this is for us, and I actually have been doing one of the initiative we're working on in this College Arts and Sciences is the AI for the humanities. So this idea embodies not only the research concept in the humanity or humanistic social science and arts, but also we hope to incentivize incorporating AI into education. So this is a very big thing, I think, in the College Arts and Sciences. And this is resonate with what a lot of things Mari said, that in education is the core of the University of Washington. Incorporating AI is not just an idea, it's a must. We have to do this because AI is here and we're definitely behind. So this new GPU or AI computing infrastructure will allow us to push the education in arts and science to a new era of AI, I would say.
Yeah, and question for Mariano and Rita. So what type of resource training and support would keep your research go further in the GPU space? Resource training and user support.
Oof, I think on the one hand, maybe some onboarding training, like on how to use efficiently the cluster, so I don't have to do it. Like, when I am an affiliated professor here, so sometimes I recruit students and getting them on board using Tillicum, that will be great. I mean, the easy question is more GPUs, but I will need to think more. I'm not sure if to be able, so we use machine learning techniques, meaning libraries, to go at the CUDA level and fuse kernels and do that type of work. I'm not sure you want to support that or that I want to do it at this stage. So in my experience, the capabilities you have are great for supporting multiple research groups, and it has, as I mentioned before, accelerated us a lot. So for the next years, I will not touch much. Like I will, like keep it, try to expand maybe and reach a broader community, and maybe through training, like make that more available. I would think more about.
I think in terms of, if I talk in terms of compute, then for me it's memory. So not like GPU memory, but how quickly Tillicum remains in terms of being able to load stuff from memory onto the GPUs and how optimized those access times remain. So that is the bottleneck for a lot of our pipelines, and that remains true for us across HPC platforms, whether that's NSF-funded centers like NERSC or DOE, stuff like them, or some stuff here. So I think support, I don't know whether there's support you can give, but essentially optimizing that, because the GPUs are top shelf. I don't know what you can do beyond H200s, but that is where I think if it's maintained, if the current speeds are maintained, that would be very good for optimizing workflows for us or for people who have workflows like us.
Thanks. Anything from audience? What type of resource and training and support you would like to see in supporting your GPU computing further? Yeah, Andy?
I wonder if you can comment a little bit on, as we succeed with Tillicum, how do you see the challenge of actually providing the storage for the data that we're going to be processing and analyzing, and the models that we're going to be building and the training sets? Do you have a vision for complementing all of the other resources that we have?
Yeah, thanks. Right. So looks like we still need to improve our user experience even further. So, but I'm pleased to say that UWIT and OR eScience are offering a series of workshops that help users to onboard GPU computing. And also, we have excellent HPC specialists led by Kristen Luscombe. Oh, sorry. Say your name incorrectly. Sorry, Kristen. That we will be helping each individual user to accelerate their GPU computing goal. And also in the storage space, we will be having other storage platforms such as Copa that user can access to support their storage needs, according to Andy's question. And for the next generation GPU computing, it looks like we need to continue investing in the space. And the next generation of GPU computer supported by NVIDIA has faster data transfer bandwidth between GPU and CPU, and which will be a bonus compared with H200. Yeah. and additional cost.
Yeah, so you guys mentioned that you used this in the early stages, so everything was fast paced, everything felt more fluid. But when it comes to like when it becomes more public and more users are going to be on it and more data is going to be on it, and larger and larger model will be built, is there resources or like things in place that would like help, I guess, other new users who are on it to reach the same speeds, or like do we anticipate that like the speeds could fluctuate given the amount of like things being run on these models? Like, is there something in place for that, I guess? Where I'm going.
So my understanding of the question, let me repeat, is that depending on how many users are using Tillicum, it's the performance of a computing node gonna vary depending on how many users are using it simultaneously. Yeah. Right. So the computer is optimized for multi-users. So that's why it's a shared resource and a supercomputing model. And very often the performance drop will not be very significant, even if multiple users using it, especially when we have a flash drive. That the I/O, which is often a bottleneck when multiple users are using a cluster, will not be a significant bottleneck for this newer generation Tillicum. Yeah, and data transfer, if multiple users are sharing one GPU node, I would speculate that it did affect model performance. However, if a computing node computing task is localized in GPUs, in one of the GPU node, then I wouldn't say that would affect performance, even if a lot of users are using very different nodes. Yeah. Okay, Xiaosong.
No, I just want to add a few things. I think I resonate. I second what Ting said, but things will change when you have more users and more data and different type of data, different usage style. But one thing I think from my experience working with the IT team, we have some of the best team here. So they monitor the performance of the system. We have one of the best HPC architect over there, Nam. So yeah, don't be ashamed. And we'll have some of the best data center, engineering here. So just trust them. They will get things done. Yeah. So.
Yeah, thank you, Xiaosong. Yeah, we do have an excellent team supporting users, regardless of whether you're using Hayek or Tillicum or computing storage. So let's now move on to the last question of the day. So let's go back to the technical side. So what's your experience like getting started on Tillicum? And is there anything challenging that you noticed so far? And is there anything that's especially rewarding up to this moment?
I would say no. So the person who used Tillicum mostly from our group was a student who was doing the work on clone. So they were using Hayek clone. And the best part of the Tillicum experience for us was we used Tillicum to do this final production run for a big inference we were doing. And that was the place of least resistance. The student had trained everything on clone. The data was on clone. We were able to very quickly move to Tillicum. And on setting up on the H200s and the compute environments was seamless for us, moving from clone to Tillicum. So I have absolutely no suggestions for improvement over there. So.
And I will bring the perspective of using an external cluster. Moving into Tillicum was extremely rewarding, really easy. You have the tutorials for Tillicum and Clone online, which as follow. You use regular schedulers, Slurm, so the experience was quite easy. I mean, we were in a rush because we have the short time of the early access, but we didn't spend any time like setting up. Like data transfer, I think Kristen said, it could be you have multiple options, it could take time. The simpler option, like terabytes of data, was fast. So it was, yeah. And on the technical side, it allows us to explore multiple models or architectures, optimize, I didn't want to say it, but given the chance of having early access, we were able to optimize the models to run like H200 have this precision FP8. We have never tried them before. We were able to use it. So in general, it was a positive experience.
Well, it's embarrassing we haven't started yet. One of the reasons is our code hasn't been able to combine because it's not because of GPU modules, mostly because HDFI. But we have a lot of experience. Been using L40S, and we have access to A100. So one of the things our code does is we have many layers of tensor contraction. So depends on the memory size. We oftentimes have to redevelop, to optimize the code. So we have to decide which tensor contraction starts first based on the memory size. So we are actively working on it. Ting convinced me that this is way more fast than NERSC because I trust him. So I'm definitely convinced that we're going to make our code, optimize the code of H200s. And I can report back next time, if there's next time for me. So, but I trust that this is going to be a fantastic machine for scientific computing.
Yeah, thank you, panelists. Is there any comments from audience? Okay.
Thank you for a very interesting discussion on the Tillicum team. Are you planning to publish any guides with rules of thumb for new projects that are about to start, maybe like computer vision with some horizon, say a year and a half? What are the benefits of going with the HIAC where you have dedicated resource, which is yours, versus not doing HIAC and going with Tillicum, where potentially there's contention and day-to-day graduate students working, they may not get the resources, so maybe burn through all the funding. Would there going to be a guide or kind of suggestions to plan ahead? Thank you.
Yeah, thanks for the question. So HIAC and Tillicum are two different resources, and they are built on different models, which means HIAC is a condo model that the PI owns the computing nodes, and it keeps operating for a few years. And Tillicum, in the Tillicum space, the hardware is subsidized by the university central, and the user acquire computational hours for their credits for computing needs. And if your task is a CPU, then HIAC will be a better platform for you. And because HIAC has CPU nodes, Tillicum has CPU, but it's a dedicated GPU computing cluster. So that's some of the technical perspective about the choosing between the two platforms. And Tillicum jobs basically need to be queued. And if multiple users are accessing it, it will be the job need to be scheduled, and it doesn't guarantee immediate run of the jobs. But HIAC offers you real-time computing capability because a user owns the node. Yeah, those are some of the consideration. But I feel in the future, maybe it will also be important for us to provide a comparison chart in choosing between the two platforms. Yeah. Thanks. Yeah, Mari.
Just to add to that, I think great suggestion. Thank you for the comparison charts. The other thing is financial. For HIAC, it's a pretty big entry cost if you want to do GPUs, less so for CPUs. And so that was an important consideration for Tillicum to allow people to get in for much lower cost.
Thank you all again for joining us and celebrating Tillicum launch. This is a big new service for the university, and it would not exist without all of you being ready to use it and wanting to work with us. And we are so eager to support you on the user support side as well. I want to thank also the vendors who we work with so closely to bring this together, and all of UWIT has played a role in this, and especially research computing division from data center, HPC engineers, the support team, and all of our supporters across the leadership. I know that research computing division wants to thank all of you. So I will say one more reminder is that posted around the room, there are QR codes to fill out a feedback survey. There is a question on the feedback survey that kind of asks you what we were asking the panelists. What are you looking for to get onboarded to Tillicum. We're building our training resources. We're building collaborations with eScience to bring more and more partnered trainings to you all. And so having that input at this early phase is critical, that we know that what we're doing is working, but also we're on track for finding the best fit for you.